Okay, so it's a pleasure to introduce Danielle Brake. She'll talk about multi-precision for polynomial solving.
Yeah, so I'm going to talk about multi-precision. Thanks for having me. My name is Danielle Amethyst, and I'm at the University of Wisconsin in Eau Claire, kind of in the middle of nowhere. We're one of the medium-sized undergraduate campuses in the UW system. So it's cool to be somewhere that has a graduate school again. I love graduate students. So I guess my first point is that we need multi-precision. So I want to talk about a few real impediment or a few real necessitators as far as multi-precision goes. So we depend on crypto to be able to communicate securely over the internet. Right? We have like in the 90s, we started to get RSA encryption for our communication through our cell phones. In some contexts, these days we depend on like 4096-bit RSA encryption or elliptic curve encryption, and all of that's done using multi-precision. So a lot of those algorithms are in some way combinatorial or depend on combinatorially large numbers, we only have to go as far as 13 factorial to overflow a 32-bit unsigned integer. We only have to go as far as 21 factorial to overflow a 64-bit integer. And then if we're working in the doubles in terms of floating point numbers, 19 factorial is sufficient to make it do rounding. So you really don't have to go that far in these numbers in order to cause you to solve problems. So just from a basic we need to work with integers perspective, we have to have multi-precision. Linear algebra needs multi-precision. So we often want to solve a linear system, and some linear systems can't be solved. Those are the singular systems, and those systems that can be solved but are difficult to solve will often require multi-precision to properly solve. And if you use a solver that doesn't use multi-precision, then you may be getting garbage back as your result. And how you tell that differs depending on the system. Oftentimes it will just fail opaquely and you won't be able to tell that the solve failed. You just get garbage back. So the burden's on the user in most linear algebra systems to tell whether you actually were successful in your solve or not. So we can define a family of matrices by the Hilbert matrices. So all we're going to do is take and fill it on the anti-diagonal with 1 over the anti-diagonal number. And right, so it starts with 1 on the first anti-diagonal, halves, thirds, quarters, and fifths, just in the third right here. So let's take a look at what if we have to invert the system, which we're not actually going to do, right? We're actually going to use like LU or some other factorization to solve it, because we're never actually going to invert the thing, because we're saying the size of the condition number grows exponentially. So we're growing linearly on this axis here, but we're growing exponentially on this axis because it's the log base 10 axis, and it's growing exponentially until eventually it hits a ceiling right here when the condition number starts to clip. So the condition number being a measure of the invertibility of the matrix. So what's happening when we reach right here? Any guesses from the audience as far as what happens when we reach that ceiling here? Does the condition number really level off?
Well, so it overflow or something.
Yeah. So we're using doubles, where you get about like 16 or 17 digits, which is where I've drawn this line right here. So as soon as you start to exceed that, it just starts clipping, and you can't even measure the condition number of the matrix, let alone try to solve it. Right? And we didn't even have to go that far. We're at like 13 or 14 by the time it becomes absolutely unusable, like beyond unusable. And really, if you want to actually be able to use the inversion of the matrix, we probably shouldn't go beyond size like 5 or 6 if we're using doubles before we start to have just catastrophic loss of precision. And that's a fairly simple matrix to write down. The magic square has the rows and columns summed to the same number. And if we measure its condition number, we experience the same clipping problem. So every other one is invertible, and then the ones that aren't invertible show up here on the top. And what's curious about those is that they all clip, but they're all actually singular. So just measuring condition number in some sense tells you whether you're singular or not, but is strongly masked by the numeric type that we happen to have. So you probably should be careful about how you measure singularity and relate it back to the numeric type that you're using when doing computations, right? Because we could, right, if we were using 128 bits, we'd be able to get up to like 34, right? It would be like 10 to the 34 would be the condition number, but it would still be actually be infinity because the thing's definitely not invertible. And then this one's curious. If you even compile software, you have to have multi-precision. Have you ever compiled GCC from source? That's a good exercise. You should compile GCCs from source sometime.
Okay.
What's really fascinating about that compiler and other compilers is that they depend on multi-precision themselves. So GCC, when you compile, it depends on having GMP installed on the system that you're on already, right? So there's a cyclic dependency problem in it, and that's why they call it bootstrapping to compile compilers. But so why does a compiler need multi-precision? For constant folding, cross-compiling from 64 to 32 bits or 32 bits to 64 bits, for loop unrolling, and other optimizations like that, where you have to count the number of iterations of things, you quickly can exceed the bounds of built-in integer types, whether 32-bit or 64-bit. So even for a compiler, even to compile your software, you have to have GMP, which I thought was a fascinating observation. And adaptive precision is the use of varying precision to let your algorithm work, but use the minimum one that you need. And we in this room are not alone in thinking about multi-precision. It shows up in all sorts of different places. This is one that's going to be close to home for at least a couple of us in this room. Intersections in algebraic curves, aggregate smoothing and trading. Here's a linear algebra application, cellular nonlinear network. So adaptive precision is definitely like a hot topic these days and something worth paying attention to. And now I have a list of titles on this slide right here, and I'd like to say that I like this one the most because it's sentence case, so I know that Jacobi is a proper noun. I generally dislike title case because you can't tell if something's a proper noun or not. So that's my like personal jab today. Okay. So I was expecting a modest amount of graduate students, so I put something in here about numeric types on a computer.
That's not helpful anyway.
Okay. So we represent numbers in a computer by strings of bits, right? By just concatenation of bits, and we interpret them. When you do arithmetic on a computer, rather when the computer does arithmetic for you, it can't possibly represent results correctly because you need like an infinite number of bits to represent 0.1, right? So at some point it has to like round or truncate in order to represent your number for you. Depending on how your arithmetic is done, you incur error. Right? So the rounding error is the error that is the result of rounding after you do arithmetic so that you can stuff it back inside of the numeric type that you've chosen to store your data. And it was only in 1985, despite the fact that we've had computers in a substantial way since the 60s, that we finally had a consensus on what rounding should be. It's also important for you to know that there are different rounding modes that you can choose, particularly if you're using external libraries like GMP or MPFR, not GMP. MPFR lets you choose a rounding mode. That's the R in MPFR. Lets you choose a rounding mode. So you can round toward 0, you can round toward infinity, you can round toward negative infinity, you can round to nearest, depending on what you need. And before 1985, people were just doing whatever they wanted, and you would get inconsistent results depending on where you ran your software, and that's troubling. So we can also incur error when we cancel. If we have two nearby numbers, and we subtract one from the other, we can experience a catastrophic loss of accuracy as those nearby numbers cancel each other out. And that, for example, can occur if you use the naive implementation of the quadratic formula, b squared minus the square root of, plus b plus or minus the square root of b squared minus 4ac all over 2a. If you just write that and c happens to be small, then you will incur catastrophic cancellation error, and your numbers will be wrong. So even what we teach our students to do in like 7th grade is like the wrong thing to do to make a computer do. You can overcome it either by using different implementations or by using numeric types that have longer representations, so it pushes the likelihood for cancellation error further back in the numbers, so you don't care as much. Hardware offers a bunch of different numeric types, and we like to call them int, so int is often 32 bits. What you should know is that int doesn't always mean 32 bits. If you want 32 bits, right, you should like specify that you want 32 bits. Like if you compile it on an Arduino, an int is 16 bits. And if you don't know that, then you can get wrong results in your software. So if you actually really do need a certain number of bits, you should really specify that and don't just depend on the compiler to do the right thing, because it probably won't. So the smaller containers tend to be about 32 bits in size, and then the larger containers, 64 bits, a long is like 64 bits, and then the double and quadruple, it sounds like a double should be a quadruple, but they're not the same, because they push around the number of bits in the exponent and mantissa in different ways. So somewhere between 106 and 113 bits. Some compilers will support those extended hardware types, and some don't, and some CPUs will support those and some won't. So if you're like compiling for Arduino or something like that, or Raspberry Pi, you should probably pay attention to what the CPU will actually run for you. So there are choices as far as numeric type, and they should be informed by the algorithm that you're going to run on them. If those aren't sufficient for you, which they probably aren't if you're in this room, then we have choices for big int, so big integer numbers. Big rat would be basically a pair of ints with the rational structure embedded on top of them. I'm cute, so I put a little like rat next to the big rat there. There are some fixed precision big floats. In particular, the Boost Multiprecision library does offer fixed precision quote-unquote hardware implementations of 128, 256, and 512 bits. And you can even fix precision, and they'll optimize for you where they can. So there is fixed precision bigger than those offered by hardware, which can be really nice.
What do you mean it will optimize for you? You mean like good multiplication scheme and all these things?
But then you're fixed to use, right? You're fixed to use that size.
Mm-hmm. Yes.
Which for me, where I want to like move up and down as necessary, it would mean ever more states and ever more transitions to write between states. So I generally don't use those types. Strangely, maybe not strangely, in like the issues pages for Boost Multiprecision, most of the questions I see people have are about the fixed precision stuff, not about the variable precision stuff. So variable precision seems more rare. Right, so I use variable precision because I want to be able to up and down the precision as necessary. And one big caution, if you happen to be writing C++ code, maybe you've encountered this already, maybe you haven't, it looks like std complex. We should be able to stuff any type we want into it and instantiate it. But if you try putting in anything higher than a double in, you're going to get bogus results at some point. The standard only provides for the std complex template type to work for built-in types. So you can't put anything custom in for T.
So it just will not compile?
Oh, it'll compile. You'll just get garbage results. Yeah.
Okay.
Particularly if you use like the arg or angle functions, or pass-through trigonometric functions.
Okay.
Then you'll start getting, right, it'll give you the right numeric type back out, but you'll only have like 16 digits correct, and after that it'll just be nonsense or zeros. But it doesn't tell you that. You have to write tests, right? So you have to unit test your code. Unit test your code. It's the only way to know. So I just wanted to put a few results, or a few resources for multi-precision on a slide, since I feel like slides should have resources in them. In particular, I found this one to be helpful. This is somebody's blog on choosing multi-precision library in C, where they tried some and shared their experience and like, what was it like using these different libraries for multi-precision? Because there's a lot of choices. And I found this top one here, what every computer scientist should know about floating point arithmetic, to be most informative. And I found that before reading that paper I was pretty ignorant. I think I'm probably still pretty ignorant. I think if I really wanted to know this stuff, I should probably like learn machine assembly code and write like an instruction set for CPU. But that's not this lifetime. So like I said, you have choices for doing multi-precision. I focus in C and C++, as far as my language choices go. So at the root of them all is GMP, and then building on top of GMP is MPFR, which lets you do floating point numbers with rounding. And they offer, also the same group offers MPC. So MPC and MPFR are kind of a pair of things. They're really similar in flavor to each other. So it's pure C, where you pass by pointer in a whole bunch of places. And yeah, I'll critique those in just a bit here when I show you some code, comparison code. And then as far as choosing a C++ library, MP-real is usable for doing multi-precision in C++, but appears to be a zombie library, because I haven't seen any updates to it since 2015, which is unfortunate. But Boost Multi-Precision is actively maintained and has a number of awesome features. Like if you don't want to use MPFR or GMP for your backend, you can write your own backend. So it's just wrappers. It's just templated wrappers. So that's what I use. I use Boost Multi-Precision for my C++ multi-precision needs. It makes it simpler. And they just added complex arithmetic to it too, which is cool. It's far from optimal, but at least it exists. Okay, so here's my complaint about just using C as a language. So this is out of Bertini 1, or out of code that I wrote against Bertini 1, compiled as a library at least. So this to me is very C in nature. So we're gonna like make a couple of containers. These comp is complex, MP is multi-precision. So this is Bertini 1 speak for a multi-precision complex number. So we're going to make two of them. And as soon as you make them, because we don't have object-orientedness in C, now we have to initialize those containers. And we're going to initialize them to be 1024 bits. Okay, so there's 2 lines of code. And then I want those to be equal to 1 and 0 respectively. So it's like 6 lines of code to make 2 numbers, 1 and 0, at high precision, which is a lot, considering I really want that to be 2 lines of code. And then I'm going to set one of them to have some particular value. I'm going to divide, and you have to know that the first thing is the result, and that the last 2 things are the operands, right? So like, one has to know something about the library in order to read the code. That unit width is the result. And then I'm done, and so now I have to clear these things. So there's just a lot of code to like basically write the number 1 over n. That's basically all I did was like, 1 over n minus 1. I have some number n, and I wanted to compute 1 over n minus 1. And it was rather heavy, and this to me is what GMP feels like, or MPFR, or MPC. They're really like line by line, which is good because you can control temporaries, because every temporary is something you have to make yourself. It's bad because this is what it looks like. As opposed to in Bertini 2, where I use the C++ wrappers, I can just go unit width equals, and then do arithmetic with arithmetic overloading, or operator overloading, and it's all in one line. But of course you pay a cost, nothing is for free, so maybe inside of whatever happens to make the division happen, there are some temporaries generated, or if you have a long chain of arithmetic that you're doing, some of those can generate their own temporaries, and you can't optimize those away and make it just be the same temporary you just reuse. Which you really should do if you can, because these things are dynamically allocated, right? So they're touching the heap. So they're expensive. They're expensive to make. Yeah, I think that's all I'll say about that.
And what do the expression templates?
So expression templates are a C++ mechanism for making this happen. So instead of returning a result, it returns an expression, and only when you're done building expressions does it actually evaluate.
So like lazy evaluation.
It's essentially lazy evaluation.
I see.
Yeah. If you want to know more about expression templates, this book right here, An Intensive Course for Scientists, Engineers, and Programmers Discovering Modern C++, has a pretty good introduction to expression templates and a bunch of other modern C++ stuff. I taught out of it one time. It was a great experience. I would totally teach out of that book again. Okay. So I refer to this thing called ambient type, which is the type that's going to be used for computations in your environment. There are some choices that you should make. Like if you have the number pi that you're going to work with, do you like get a copy of pi at the maximum precision you're ever going to use and then just downsample from it? Or do you compute it as needed? Do you keep many copies of pi so you only have to ever compute them once and go look them up? Right? So like, how do you deal with getting numbers into the right precision for the ambient type that you're going to be working in? Should we be at precision just sufficient for the current level of accuracy? Should we be pessimistic and like always keep like 10 more digits than we want? And I do tend to think in terms of digits rather than bits, because boost multi-precision refers to things in terms of digits, not bits. And one big question that you should ask yourself is, are you ever gonna work in a case sufficiently simple that you should just use double? And if so, how do you glue those things together? Furthermore, if you've computed a result, you should probably know something about the precision that was used to compute it, so that if later you have to change its precisions, you know something about the number. I think you should measure the accuracy of the thing. Right? So like when we compute a number, we should have a statement about the accuracy of the thing and then carry it around. But then I have to carry around a bunch of other like metadata for my numbers, which can be cumbersome and burdensome. And that's one thing I feel like that Bertini 1 does poorly, is keep track of precision for previously computed results. It's challenging to keep track of those things, but you have to have metadata. Right? You have to have metadata.
Would intervals be enough to hold that, give you the same information as?
Yes. So I think the intervals, well, because they necessarily contain the thing. They necessarily
or the
contain
center graph of information where you have center plus an error. You carry that around. That's very cheap.
Yeah. Yeah, it's roughly somewhere less than 2x more expensive than not doing intervals. Is that right?
Well, it depends.
Michael Burr is quite good at intervals. Okay. So I have worked in the world of Bertini where we switch numeric types from double to multi-precision and back and forth. And we talked a little bit about this in our conversation before my talk today. So I posit that it's not trivial to write an algorithm that uses multiple numeric types. I believe that it's an inherent challenge in terms of decision making for like where you hold the duplicity. So you're going to switch numeric types. So at some point you have to have both copies of your data. You have to have your data in both double type and in multi-precision type, and be able to move back and forth in those things. So if you're going to have a variable, a multi-type algorithm, do you pass those two types into the algorithm and then it figures out how to change between them, or do you write the algorithm so it uses one type and then you pass back and forth the data between the two types at some higher level? Because they have real design consequences for that. Right? So you're playing hot potato with your numbers, and at what level do you want to play hot potato? But you definitely have to if you want to use multiple numeric types. So do you use a state machine, something not as flexible as a state machine, but that's more tailored to the algorithms that you're going to use? And then how do you store these things? Do you store, right? So you're gonna have a number in two different numeric types. Do you couple them together so that one number in two different types looks like one number? Or do you let them live separately from each other, in which case you have like wholesale duplication of your data in two different locations? One's I don't think necessarily better than the other, but they definitely have implications as far as program performance, as well as ease of writing code.
This sort of depends on how often do you want to synchronize them, right?
Yeah. In my experience, you should try to synchronize as rarely as you possibly can, which is probably an obvious statement. But you should probably not couple them together for every individual number, because then you don't get to have arrays of a simple type. Particularly, like if we have doubles, we should just have arrays of doubles.
That's true.
Because we can just, like we can just malloc or new a block of those, and they're all adjacent to each other in memory, so that you're going to achieve better cache locality, as opposed to you'll fragment your cache if you don't store them together. Yeah. Okay. So another question that you have about type switching or about variable precision is if you say are at precision 50 digits and you want to go up to like 70 digits because something told you needed 20 more to be able to do your thing. Now you're going to add 20 digits onto the back of all of your numbers that you're going to use for computing. How do you populate what those last 20 digits should be? Like, should you just populate them with zeros? Should you just populate them with noise? Should you do like a Newton iteration on some other system to be able to compute what those last 20 digits are? It kind of depends on what the context is, right? If they're the coefficients of your polynomial system, then those 20 digits have to be correct. If those are just like the current state of the current state in an iterative process that you're solving, then probably the next iteration will populate them anyways, so that will be the sharpening itself. But I don't think that you can be ignorant of what happens when you increase precision, because you need to know whether those 20 digits are going to be reasonably correct or not. Right? And then I have a note here on implementation, how you represent the state of the precision compactly. So you have a bunch of numbers, and they probably all report their precision to you themselves, but in some cases they don't. In some cases you have to keep track of what the precision is.
You mean how many of the digits you have are reliable, or?
Yeah. I guess that'd be a statement of accuracy more than precision. Yeah. One of the most unfortunate things about using multi-precision, in my experience, has been the lack of parallelization and other issues. In particular, I'd love to use GPUs because they're both massively parallel, but there are no GPU implementations for MPFR or GMP, and so if you want to work on problems that require more than double or even single precision, you're dead in the water. There is a group in Chicago under Jan Verschelde that has done work on computing in extended hardware types on GPUs, but full variable precision on a GPU is still not even over the horizon. It's not even a possibility in a remote sense right now. But still, it offers some, right. So if you can solve your problem in double precision, and you can pass it over to a GPU, you win. And then at some point, you're just dead in the water and can't do that anymore. However, right, most computers that have like big access to GPUs, that's what they do, and then those machines themselves aren't big clusters. So like switching back and forth between CPU parallelization and GPU parallelization itself is not a good solution either. So it's not a simple world. It's not a simple world at all. And I do have a note about thread safety up there, that you should probably know whether your library is thread safe or not. GMP is. It's okay.
And boost?
Yes.
So what is this thread safety?
If you have multiple threads, is there state that's shared between those threads that will cause problems? So do they both depend on? So maybe a library uses a cache. And not every thread gets its own copy of a cache, in which case there could be a race condition to either read or write to some part of the cache. Yeah. So can you multi-thread your application without it being broken? Yeah. And it's actually surprisingly easy to write thread unsafe code. And threading is surprisingly challenging.
In this case, as an outcome, you just get a wrong result, or
it depends on the type of problem that you have. So wrong result would be, I think, like that's kind of worst case scenario, because then you don't know that something went wrong, right? The kind of best case scenario in my mind is like a deadlock, because then it's obvious that something went wrong, and you can go and find it. So give me hard locks and crashes over silent failures any day of the week. But yeah, there's no general characterization for the types of bugs that you can get from thread safety problems. Ideally crashing. Yeah. Okay, so that was a lot of like basics of multi-precision. And so I wanted to talk about a couple of applications where multi-precision is absolutely necessary. These are coming from my experience. So I want to talk about straight line tracking in the context of homotopy continuation and games, which are a way of finishing off a straight line tracking where you want to end at a singularity, but you never want to like solve an ODE all the way to a singularity because you'll never finish. And then finally, certification, which is a way for proving that you were right at the end of doing a numerical computation. Okay. So, who has never seen a homotopy continuation algorithm before? Nobody. Okay. So everybody's seen it before. Okay. So I can just be like, here's a homotopy H of ZT, where Z is the grouping of variables that we're going to solve over. T is a time variable, which is probably complex. I don't know. It depends on whether you're doing real or complex time. So we have a homotopy equals 0. And that's spectacular because if you take a time derivative of the thing, then you end up with a statement that H times z sub I dot equals 0, and that immediately emits a way for us to advance through time. So z dot, the way that z changes with time, with t here, is given by negating the Jacobian of the homotopy. So J is the Jacobian operator. So we take the Jacobian of the homotopy, so that's JH. We invert it numerically. We're never actually going to invert the thing. And multiply by H dot, so the time derivative of the homotopy. And it's pretty straightforward, right? All you have to do is compute a time derivative, compute the space derivatives, solve the space derivative matrix, times it by the time derivative matrix, negate it, and you get what the time derivative of what the space variables are supposed to be. So you have a way to advance in space through time, constrained on this level surface, or this level, whatever it happens to be, which we call H. So H emits something, huh?
And where is the derivative of H with respect to T, the partial derivative?
That's H dot.
No, that's Z depends on T. I don't understand the differential equation that you're getting.
This one right here?
No, the one on top.
The one on top here?
Yes.
Okay.
Give
Give me a second.
I think there might be sign missing.
I think there's an SIGN sign missing. So
Because basically what you have is like H dot
No.
plus HZ z dot is equal to 0.
Is that what?
Yep.
Okay.
Yep. So that first equal sign is supposed to be a plus right there.
Okay.
Yep. Sorry.
No, now we have checked that we know what the homotopy computation is. So it's a big move.
Okay. So if you want to integrate through time, right? We just want to integrate z dot, and we can move through time, and we get what I think of as the classic homotopy continuation picture, where we're going to start with some start system G, and we're going to deform through time. So the coordinates of these points up here are z's, so we're stepping through it because z dot, all we have to do is invert our Jacobian and multiply it by the time derivative of the homotopy, and we end up at least as far as the endgame boundary, and we'll come to what happens after the endgame boundary when I want to talk about endgames. So even in doing this, you have to have multi-precision to do it. You can't, in my opinion, not use multi-precision and do this process. Here's a diagram from the now decade-old paper called Step Size Control for Path Tracking, which the Bertini team affectionately calls AMP2. That's adaptive multiple precision. It's the second in that series, so they call it AMP2. Note to you, if you want to read about this stuff, I would just go to AMP2 and not read AMP1 first. AMP2 fixes a lot of things. So this is a diagram that shows the log of the condition number, So here is time equals 1, time equals 0, so we're tracking from right to left. And things are like looking pretty good. Log condition number is like 2-ish, so that's no problem. But then the condition number spikes to about 10 to the 12.
Condition number of Jacobian, right?
Condition number of the Jacobian. Mm-hmm. And so if you're using double precision, by the time that you reach this time point right here, you're at best going to have 4 digits of accuracy after taking a step, which probably in many cases is enough for you to step off the path and for something to go wrong, right? You'll encounter path crossings or something else troubling is going to happen. So even well before we get to the end game, which would happen near 0, it's clear that we absolutely need multi-precision to overcome problems like this. And this is after using the gamma trick too. So the gamma trick ensures that there are no singularities on your path. But they might be really close. So here a singularity was close.
But still, there are finitely many singularities, right? So gamma tree could ensure that we are pretty far off from all of them, or.
But it's random, right?
So it's not okay. So they can be like too dense to be easily avoided.
We don't have good estimates on that.
Okay.
Yeah, we would like good estimates on that.
I see.
Yeah, it'd be nice to know that the number of singularities grew slower than the dimension did, so that if you were just in higher dimensions, right, there were like less landmines to run into that caused this problem. But we conjecture that that's not the case. That the number of landmines actually grows faster than the dimension grows. So it gets more and more challenging to do this. There's still a finite number of them, so the gamma trick always works. But it only guarantees that it's not exactly on the path. It doesn't guarantee any distance away from the path, except it's not 0. Yeah. So I don't know that I need to do this slide for this audience. I like this slide more. But I don't know that this slide is necessary for this audience either.
What's this about?
So this slide is I cannot operate that from the side. Trackpads from the side don't work. So this slide is a flowchart description of the predictor corrector method. Right. So like purple means purple is like a step that you like want to do and you have to do to move forward. So we're going to predict to try to move forward through time, but then we're going to be off of our path, and so we're going to correct and try to step back onto the path because we know something's equal to 0. So predict is just ODE, and then correct is like use Newton's method to step back on, right? Because Newton's method is a great way for solving something equals 0, and the homotopy equals 0. So we'll Newton correct it, and if that happened to be a good step, then either you're at time equals end and you can just be done with tracker success, right? You can just be like, yeah, tracker succeeded. Or if it's not, then you can check whether we can decrease precision.
But how do you like measure that the step was good? How do you measure the success?
That is a good question. So that varies depending on the package. More or less, you watch the linear algebra. So all of this is done via linear algebra, and basically you watch whether linear algebra fails. You monitor the condition number of the Jacobian. So let me skip forward to the 3 criteria that are put forward in the adaptive multi-precision papers. So this is a statement about when do you need more precision. There we go. Okay. So there are some cryptic symbols in here that I'm not going to decode for you, but rather I'm just going to let it suffice to say that you watch the current digits, and then you would watch the, let's see here, I think S1 is going to be the step size. No, that's the current number of digits. And then we're going to log base 10, and we're going to measure the matrix norm, the inverse of the Jacobian, and the regular Jacobian, and then there are 2 parameters in here, epsilon and psi, that are user set numbers that control that control how this thing runs. So what you want to do is you want to bound the error on the Jacobian with epsilon and psi, and then you compute this thing right here, and you watch whether your current digits happens to be less than it. And if this criterion is violated, then you either need to take a smaller step size, or you need to increase your precision, or possibly both.
So this is the criterion for good or bad step.
Yes.
Okay.
Yeah. So you watch this criterion, and in particular, we would use this criterion both in predicting and in Newton's method. So both in the predict and the correct step. Whereas this one right here is used in the correct loop. So it's another statement about you measure the current digits, and then there's this. So I put D right here because I didn't want to write this all. Try to write this all in one line. So this this other thing that essentially measures a condition number. And then here we actually get to incorporate the tolerance. So that's how tightly we want to track the path. So that's a user settable tolerance. And then we have to take into account the Newton residual. So how far off do we believe we were when we took a Newton step? So so keep track of where you are, take a Newton step, and measure the difference between those two things, and that's a proxy for how far away from a root you are, right? Because hypothetically, it's going to converge quadratically. Yeah. So there's another criterion that you can use, but it's fundamentally built off of condition numbers. And a third one that looks basically the same. They vary subtly from each other. Yeah.
But like, the idea is to use them all simultaneously, or just choose one and stick to it.
You use them all. So you check the first one, and if it passes, then you would check the second one, and if it passes, then you check the third one, and if it passes, then you had a good step. Right? And as soon as one fails, you stop checking.
Okay.
Yeah. So you want all of these criteria to be true in order to say that you had a good step. So it does induce some overhead, and like definitely as far as measuring the norm of the Jacobian and the norm of the Jacobian inverse, you should probably like compute those only once and then reuse them multiple times because those are expensive to compute.
But you need to update this on each step. You mean you
But we have to do
compute
this
once
on
for
each step.
first step?
Yeah. Yeah, once per step. Once per predict and once per correct. Yeah. So cache where appropriate. Memoize, right? I should memoize. So I think multiprecision is pretty fabulous. I mentioned AMP2 earlier. AMP1 and AMP2 are closely related to each other. You can implement straight out of AMP2. AMP1 is not implementable. And the book Numerically Solving Polynomials with Bertini is pretty decent. You can implement out of it also. At least it gives good advice and good more casual summaries than the analysis that really comes in AMP1 and AMP2. Okay. So the next thing I wanted to mention are endgames, and I'm going to go till, what time am I going to go till? 4?
Maybe then 4 to 10. 5 to 10.
Okay. Okay. So here's a circle, and this is an image I made with Bertini Real, which is my curve and surface decomposer. And this image is related to the cycle number, which we're going to use in the endgames. So we want to know something about the Poisson series that represents these curves. So I want you to look at the way these points are spaced, and you might agree with me that as far as them being on the circle, these points are suboptimally spaced, right? Because they do a really poor job of representing the circle near points 1 and 2 here at the poles, at the boundaries between the cyan and the blue pieces of the curve. But if you project all of those points onto the line right here that goes down the middle, they're equally spaced. So they're equally spaced in terms of projection, but not equally spaced upstairs. So as far as taking steps toward a singularity, which we're doing as we track down the curve to one of these poles here, you shouldn't do so by taking the same step size, right? If you're approaching a cliff, you should do so by taking smaller and smaller steps. And the way that you space your steps as you're approaching a cliff should have something to do with how sharply the cliff drops off, right? So in particular, this is a cycle number 2 curve. The singularity here has cycle number 2. And so we should approach it by taking quadratically smaller steps as we approach the outside. Adding more points doesn't really help, so taking evenly spaced things. But if I rescale my spacing on the projection as I approach, because I'm controlling the points on these two curves with this invisible line that I didn't draw that connects these 2 points right here. So I have a laser pointer that points up toward the curve, and I'm approaching down here, and that induces tracking on this curve right here. So if I adjust that by the cycle number, then I can approach it and get now a more uniform approximation of the circle with its points. So I just wanted to give that not as a definition of the cycle number by any means, but just as a motivation for the cycle number clearly makes the circle look prettier if we use it. So this is related to the concept of an endgame, which is a tool that's used to compute singular roots of homotopy. So we shouldn't walk all the way to a singular root when doing a homotopy because the homotopy requires us to solve the linear system given by the Jacobian. Right? So we're solving a linear system, but that linear system is becoming more and more singular as we get closer and closer to the singularity. So we better not try to track all the way there. We better stop early. And that's what the endgame does for us. So I'll let you take it as fact that the path that we're walking, the homotopy path, is a Poisson series in T. Every variable, every coordinate of that thing could be written as a Poisson series in T. And what we're going to do is we're going to compute coefficients of that Poisson series by doing Cauchy integrals around t equals 0. That's going to be our method. Because the constant terms in that Poisson series are exactly the values that appear, are the coordinates when t equals 0. Because it's a Poisson series in t, so when t equals 0, we pick up the constant terms.
What is the function you integrate?
It's given implicitly, so that the function that we're going to integrate here, f of what we're calling f of s, is the coordinate z as an implicit function of t. So I don't know what that function is, but I can compute its values by walking a path. Right. So f is precisely in this case the coordinate values for a homotopy path as a function of time. So what we're going to try to do is compute the coordinates of t equals 0 without actually walking there by using the trapezoid rule, which converges exponentially with the number of points that we use when we walk around the circles. And it gives a picture that looks something like this. So we're coming in on this path from the top of the diagram toward the center. And then I don't want to walk all the way toward the center, so we're going to walk instead on a polygon. It's a periodic loop, and we're going to walk around it, and then we're going to compute, this integral right here. And then we're going to go down closer, and we're going to do the same thing. And if we get the same thing twice, then we believe that we're done, right? If the difference between our two consecutive approximations is smaller than our tolerance, then we believe that we've actually computed the root. And if we haven't, then we're going to go even smaller. And if at some point it's going to stop, or we're going to run out of something, right? We're going to run out of precision or hit a hard wall in some other settings. So I'm pretty proud of this diagram that I made. So I compute things with my program Bertini Real, and oh yeah, MATLAB crashed when we were playing with. I'm not gonna open this diagram. Sorry. If MATLAB hadn't crashed, I would do it, but we'll let this suffice. It's not great in comparison to the diagram. I was gonna show you where I could rotate around the sphere, but that's why I put the slide in case MATLAB crashed. Okay, so there's a sphere. Do you see the sphere inside of this tangled ball? Mm-hmm. Yeah. And then the paths that are approaching the sphere here are the 78 paths that are used when Bertini Real computes when it computes a sphere, and it does so by doing regeneration and a bunch of homotopies. And what's really interesting is to look at the condition number of these paths.
Just to clarify, the goal is to get intersection with a hyperplane, right? Or
The goal is to essentially compute a roadmap
roadmap. Okay.
of the sphere.
Mhm.
Yeah. So if we look at the condition number for steps, so I just did a histogram. So the count. This is just the number of steps that had a given condition number. So the condition numbers get pretty bad. So like we've got condition numbers on this diagram all the way up to like 10 to the 7, and then if you like there are random numbers in here, so sometimes it gets even bigger. On this one right here, we're going to track from 1 to 0. And we can see that most of the bad condition numbers happen right around the time that the tracking would terminate. That's when we're using the endgame, right? And even in computing a stupid sphere, it's just a sphere, we achieve condition numbers on the order of 10 to the 9th. So even to compute a sphere, double precision is dodgy, which is, in my mind, really surprising.
But
maybe it means that this is a terrible method to choose.
But people did it before with double, right? And
I mean, I can compute it competently with doubles. It'll do it. It's fine. Yeah.
I'm sorry, can you back up a little bit?
Yeah.
What do you mean you compute a sphere?
So this is where I wish I had my diagram in MATLAB. So what I do is I compute. I'm gonna touch chalk. Oh, I hate touching chalk. So what I'm gonna do is I'm gonna compute 2 points that are gonna end up being antipodal, and then I'm gonna compute that, and that's the waist of the sphere. So the sphere projects down to a plane. I don't have a different color of chalk. So the sphere projects down in a plane to here, where this direction right here would be like pi 1, and this direction would be pi 2. So we're projecting in two arbitrary but orthogonal directions. And then there are critical points in terms of a projection onto pi 1 of this curve. And so that point corresponds to that point, and that point corresponds to that point. And then halfway in between, these 2 points correspond there, and now I'm going to cut my surface at every critical point, and halfway in between every critical point, and I'm going to obtain another point up here and another one down here, and they're going to be connected like that. It's not my best drawing of a sphere ever. I'm supposed to have a computer diagram to help me with it. So I'm computing a roadmap of the sphere.
What are you given? What's the data?
The data I'm given is
Equation of the sphere?
I'm given f of x, I'm given pi 1 and pi 2, and I'm given a witness set for the sphere. So I take in witness points, a witness system, and witness linears, and I use the process of regeneration to solve a bunch of related systems to f that give each of these points here.
What is the f?
F in this particular case would just be x squared minus y plus y squared plus b squared minus 1
Okay.
implicitly equals 0. So that's what I'm given.
I see.
Yeah. And then there's a set of witness linears inside of here. So I have my witness linears, my points, and then f appears inside of here also.
What does that mean?
Which part of it?
Linear, witness linear. What are those?
So, if you take an algebraic variety of dimension d and you cut it with an arbitrary complex linear system of size d, you get points.
Right.
These are those points. So these are the linears that you cut it with. These are the points you get as the intersection, and this is the stuff that complements L to make up a full dimensional system.
So that's given to you?
Yes. And this part here comes from criterion. In particular, its numerical irreducible decomposition algorithm gives me those points.
Oh, those are points you're beginning.
Yes.
That you begin with.
Yep. And these points are complex points. And I want to extract a roadmap of the real points in the algebraic variety.
And you have to generate new points.
Yeah, and I have to generate a bunch more points, right? In particular, I need to generate these 6 points. And it takes a total of 78 paths to do that. Because you have to do some regeneration to build up to solve these points. In particular, like this point right here satisfies f, and then Jacobian of f concatenated with pi 1 and pi 2. Nope. Jacobian's out there. And I take the determinant of it, and then I've got that one more time to pick up this thing, and I'm not going to write it down. So this whole thing inside here, and then I take determinant of Jacobian of that whole thing, and this whole thing describes these points. So it takes a two-step regeneration process to build up and solve these points. So this is an insanely complex way to compute spheres, but the point of it is that I can compute curves and surfaces in an arbitrary number of dimensions. Okay, this works in an arbitrary number of dimensions, not just 3. Okay. Like here's a Whitney umbrella, and it's 1,800 points.
Also in 3D, right?
Yeah, it's also a 3-variable surface. Yeah. To compute the Whitney umbrella, it looks like mostly we're experiencing condition number like 10 to the 3, 10 to the 4, which is fine. I can deal with that, no problem in double. But like if you look at what's happening as we approach t equals 0, that's when we're going to be computing these points here. Like these points that are the critical points of the critical curve, those are the nasty ones. And we hit almost 10 to the 30 for the condition number when computing those things. So it's brutal. So to do this algorithm really requires multi-precision. It really does. It really does. I think that was the point I wanted to make with these slides. That in order to compute these points, these critical points of the critical curve, you have to use endgames because they're singular points. They're singular points of a homotopy. And you have to use multi-precision to compute those with an endgame. So not only do you have to use multi-precision, but you really should use endgames whenever you possibly can.
But what if you use, I forgot, how do they call it, when you construct an extended system? There is a trick, how's it called? Flattening or?
Deflating?
Yes.
Yes, so...
Will it cure the condition number or
no,
migrate there?
It doesn't. So so if your system isn't deflated, then the condition number is going to be exactly infinity.
Mm-hmm. Okay.
Right, because the Jacobian is singular there.
Yes. Okay.
So what you do when you deflate is you add additional polynomials to original polynomial system, with or without additional variables, depending on the flavor of deflation that you want. I have this in other talks that I've given, but not in this one. And they give you back a full rank Jacobian that's not going to be square. So then you have to use methods for like overdetermined systems or randomization or something like that to deal with that problem. So singularities are a problem no matter what you do, right?
Okay.
So you use deflation when you're dealing with positive dimensional singular components, embedded components. So you deflate those. And that's in fact what we do on is it shown in this diagram? Let me see if I can point out to you on the right-hand one here, this off-colored line, this off-colored vertical line is the handle of the Whitney umbrella.
So it's actually a component.
It's an embedded singular component and we deflate it to make it trackable.
I see.
Yeah. But tracking on it it's brutal. It's brutal. But some singular curves take multiple deflations. Like I've encountered some that take like 4 deflations, at which point the polynomial system is almost 1,000 polynomials long and 3 variables, and the thing becomes almost untrackable. Even evaluation of the stupid system is absurd. It's a suboptimal implementation of deflation for sure. You don't need all of those polynomials, but it's what we have. So you have to use multi-precision, and you really should use endgames. Do I have time to do one more, or should I stop there? I feel like I started almost an hour ago, so I feel like I should stop there.
It's up to you. Up to you. Maybe.
I think I'll skip this one and go to. I think I'd rather conclude rather than try to stuff another content into the back here. So a lot of what I talked about has to do with condition numbers, and that you really need to watch the condition number of the problem that you're solving to know how much precision you're supposed to use. At least as far as the work in this particular context. That's how we check how much precision we're going to need, is by the condition number. But there exists more than one notion of condition number. In the work that I've shown, and in particular in the Bertini family of products, you look at the ratio of the largest singular value and the smallest singular value, and that's a condition number. But there are other condition numbers, and Paul Breeding has been working on a Julia package called Homotopy continuation.jl, and he has been doing research on other condition numbers. And his homotopy continuation package is very attractive. Julia is just in time compiled, which is pretty swell.
But when you say better in sense of they're faster to compute, or they give you
better estimates.
Better estimates, okay.
Mm-hmm. Better estimates. Mm-hmm. And then I think my second point here that I wanted to make is that multi-precision arithmetic is slow, no matter what you do. Some libraries let you configure them to use stack memory instead of heap memory, so then you can at least partially solve the dynamic memory allocation problem, that touching the heap is expensive, but touching the stack is fast, at the risk of going out of memory faster, right? Because you have far less stack memory than you do heap memory. You have just basically infinite heap memory and very little stack memory. But some libraries will let you do that, so that is an option.
By some libraries, what?
Boost multi-precision.
Okay. I see.
And then I have one other thing I wanted to say, which is there's this one subtle issue that you should pay attention to if you're going to do multi-precision work and deal with numbers and different precisions from each other, which is you should know how numbers of different precisions interact with each other. So this issue is one that I raised on GitHub, and in particular revealed discrepancies in behavior of boost multi-precision when they have expression templates on and off. So if you just flip a bit when you compile, right, change an on to an off, you get different behavior. And it was disturbing. Because I would write tests against one, and then I would change it, and then those tests would now fail, and then I could write them to pass against the other thing, and then I'd switch it back, and then they would fail again. And I was like, what's going on here, John Maddock? And it boils down to this test right here. So I just want to leave you with this particular test as a takeaway message. You should know what would happen in your software if you were to run this code. Okay? So I'm gonna make a precision 30 number and a precision 50 number, and a precision 70 number, which is gonna and I'm gonna take the 50 and the 70, and I'm gonna do something with them, in this case add, and I'm gonna stuff them back into A. So I have 3 different numbers, all of different precisions, and I'm going to do arithmetic with them and on B and C and stuff them into A. And then the question is, what is the precision of A at the end?
Should be 50.
Should it be 50? Why?
Well, it's the smallest of the summands.
It's the smallest of the summands?
Yeah.
Okay. But the precision of A was 30. So now A's precision magically changes?
Ah, okay, it was defined. Yeah, okay, that should be 30.
It depends, right? One could take one convention over another. And so I put a name to these 2 different concepts last year. Assignment preserves precision of source, so that if you were to do this thing, and I unfortunately called them A, B, and C are different here. So before A was the result, now C is the result. So we're going to do arithmetic, and the precision's going to become 40. In your case, it would have been 50 on the previous slide right here.
But why did it become maximum of the precision of A and B?
So here it's the minimum of the precisions. No, it is the maximum precision of A and B. So there are probably additional choices to be made as far as being conservative here goes. It probably should be 30, shouldn't it? I don't know. I think this is like an endless debate.
Well, I mean, if it's 40, then you don't have guarantee like that less than 10 digits
Are going to be
can
inaccurate.
anything.
Yeah.
Okay.
Yeah.
Well, that's also
Yeah.
fine.
Okay. The point was that it overwrote the precision of C.
Mm-hmm.
Right.
Mm-hmm. Yes.
It was 80 and now it's 40, but here it's 80 and then it's 80 at the end. Mm-hmm. So C was the target. So assignment preserved the precision of the target, and assignment preserved the precision of the source. And you don't know which of those two things it is until you've read the code or read the documentation and believe that they actually do that. So what I encountered in Boost Multi-Precision last year was neither of these, and I got different behavior with expression templates on and off, and it was disturbing. So you should know if you're using a library, does it preserve the precision of the source or the precision of the target? Right? What's the precision of your result going to be? So the answer is, as of this commit, Boost Multi-Precision preserves precision of source, and the precision would be 40 after doing this. Mm-hmm. So it's going to inherit the greater of those numbers. Right? And I'm not the library author, so I'm not going to make that change. Mm-hmm. So if you wanted it to be 30, it's 40. And I'm going to say thank you for your time today.
Thank you. I have a question. So in your abstract, you mentioned also the problem with probability one things in the choice of gamma.
Mm-hmm.
So do you mean to like use multi-precision number for gamma to have like how do you choose precision for gamma to have decent probability? Because or it's not what you.
I don't think that's what I meant. I think what I meant is that you choose a gamma and then it kind of sets up a profile like this
Mm-hmm.
for you that you have to deal with.
Okay.
I think that's what I meant.
Did you want to make a point of making gamma multi-precision number?
Oh yeah, it should definitely be a multi-precision number.
Uh-huh.
Yeah. I mean, if your system that you're working on is going to be multi-precision itself and go up and down, because gamma isn't part of the system, it also needs to go up and down, right? So in some sense, you need to like hold authoritative values of your numbers,
mm-hmm.
and then downsample from them to the current working precision as necessary. I don't think I answered your question.
Yeah, but yes. Just to clarify, so are you proposing to? Okay, so I just see two ways: generate gamma like maybe as random double and then make it multi-precision, or generate it as very random multi-precision. So do you want to introduce extra randomness or
the second thing?
Second.
Yeah.
Okay. Thank you.
Where right now, I think what I do is I take the ratio of two 50-digit numbers.
Integers.
Yeah.
I see. Mm-hmm. Okay. Yeah, thank you.
So what's the word end games mean?
So it's a term coming from chess, and as you're tracking from your start time to your end time, you get close to the end time, right? And think of it as you're like playing a game. So this is just doing this process is playing a game. So when you get close to the end, you're in the end game. What we mean by end game is something that spares us from tracking all the way to the singularity, right? You don't want to track all the way to the star because the Jacobian is singular at the star. So the problem becomes more and more challenging the closer and closer to the star you get. So by using an endgame, you can use an alternative method to compute what the star is without actually tracking all the way to it.
Other questions? Let's thank speaker again.
Thank you.